So now that you've got a chance to understand the streams model at a high level, let's start talking about some of the common streams operations that you're likely to encounter in practice. And some of these operations, which we'll talk about first, are ones that create a stream, so they're essentially factory methods. And then we'll also talk about some of the common aggregate operations you'll find in a stream. Now, this introduction is by no means exhaustive, and there's plenty of other operations that we'll come across later as we get into the details, but I want you to get a kind of a high level view of what's going on here. So there's a bunch of factory methods that create a stream from some source of data. We've seen this example already. This is the OfFactory method, and you use the OfFactory method to convert an array of elements of some generic type T into a stream of elements of some generic type T. In this particular example, we're going to start out with an array of strings for the characters in Hamlet, and then we're going to turn that into a stream of strings. So the array of Horatio, Laertes, Hamlet, Gertrude, Claudius, whomever, Ophelia, those things get turned into a stream of these strings. And that's what one thing you can do, and of can be used to do that. There's a whole bunch of other factory methods, though. You can see there's about 24 of them, in fact. We're going to focus on the ones here on the left in a lot of detail. So we'll look at stream and parallel stream. We'll see some fun examples with split as stream. We'll take a look at the of method. We've already seen that. We'll also talk about something called stream support.stream, which is useful when combined with something called splitterators. And you'll see that as part of your upcoming assignments, you have to implement splitterators. I think grad students do that in assignment 1B. Undergrads do it in assignment 2A. And then there's a bunch of other factory methods too we won't spend as much time on, but we'll cover them a little bit. So let's talk about the aggregate operations next. So if factory methods create stuff, then aggregate operations take stuff that's created, streams that are created, and then perform behaviors on the elements in a stream. And we'll see that this behavior is implemented by a lambda expression or a method reference, something that corresponds to one of those so-called functional interfaces we talked about earlier in the course. Here's a very, very simple example of this. You can see that we have a stream of the characters in Hamlet, and we're going to apply the capitalized method reference, and that's going to go ahead and put the elements in the stream into some canonical capitalization model. And capitalize is a method reference that's passed as a parameter to the map intermediate operation or aggregate operation. We'll talk more about the difference between intermediate operations and terminal operations, but intermediate and terminal operations are both examples of so-called aggregate operations. And the reason they're called aggregate operations is they work on a group of things, namely the elements in a stream. Some aggregate operations perform behaviors on all elements in a stream. And you can think of these as basically being kind of a run to completion style model. So they just keep running until everything's processed. Other aggregate operations perform behaviors on some elements in a stream, maybe no elements in the stream, depending on the characteristics. And these are what are typically called short-circuited operations. So we'll talk more about the difference between the run to completion operations and the short-circuited operations later. But for the time being, just be aware that behaviors are applied to elements, either some or all, in a stream. And that's what the aggregate operations are responsible for doing. You can think of this, when I like to think about a stream, I think about, or stream processing with aggregate operations. The mental model that comes to my mind is a water pipeline filtration system. So if you live in an area that may have not the best water, like Flint, Michigan, or some other place, hopefully you don't live in Flint, Michigan with its problems with water, but if you live someplace that doesn't have the world's best water, you might have a water filtration system. And what happens, of course, is a stream of water, literally a stream of water, flows through a series of filters, and those filters then remove impurities from the water. And hopefully what comes out the other side is pure drinkable water that won't give you all kinds of bad illnesses as a side effect. This is also commonly known as a pipeline, and we'll talk more about that if those of you who may be familiar with things like the Unix or the Linux shell. Those are also examples of pipelines as well. In the context of Java streams, as opposed to water filtration systems, the output of one aggregate operation can be input into the next one in the stream. So we're basically connecting things up. the output goes into the next input, and it just flows through the stream pipeline. So here's a simple example. You can see this. We're pipelining together the stream methods of, filter, map, sorted, and forEach. And the way this works syntactically is by using a cool mechanism known canonically as the fluent interface pattern. And fluent interfaces have been around before Java streams, but the concept of fluent interfaces is a very popular pattern. You see this used all over the place in practice. And so this will be something that you'll just have to get used to. If you want to read more about the fluent interface pattern, take a look at the link at the bottom of the slide. But basically, let's kind of look at an example here. So we start off our processing by having the of method. And as we saw before, of takes an array and creates a stream. And we'll talk more about that in some upcoming discussions. And then of is connected to, the output of is connected to the input of filter. And so this is that fluent interface. We're just kind of chaining these things together by using the dot syntax, just making the method call. And filter then in that case is going to return a stream that contains only elements that match the predicate. And of course, we learned about what a predicate was when we talked about functional interfaces, and you saw that a predicate basically performs a test and returns true or false. So if the test that's applied here as a behavioral parameter returns true, in other words, if, for example, it's a uppercase or lowercase h at the beginning of the name, then it gets to go through the filter, otherwise it gets discarded. And then that gets connected to and piped through the map intermediate operation. And that returns a stream that consists of the results of applying the mapping function to every element in the stream. So in this particular case, we're going to capitalize the elements so that they have a canonical capitalization scheme where the first character is capitalized and everything else is lowercase. The next operation is sorted. So after we get done mapping everything to canonical capitalization model, then it goes through sorted and it arranges it, in this case, to sort it in ascending order. You can also sort it in descending order if you want to, and do other kinds of processing as well. But in this particular case, we're going to sort it in ascending order. And then the final result, the output, the sorted output of properly canonically capitalized characters in Hamlet that start with the letter H, those will then be handled by the forEach terminal operation, and that will go ahead and print each element to the standard output. Notice again, and we'll talk about this more as we go further into the discussion about terminal operations, nothing gets done until the terminal operation starts to run. So the terminal operation is what kicks everything off. And this concept of lazy processing is very, very common in stream-based programming environments. So we'll see it here with Java streams, and we talk later about reactive streams and frameworks like RxJava and Project Reactor and so on. You'll see that they're lazy too. They're just lazy in a different way. And when we get to that point, I'll compare and contrast Java streams with reactive streams. And you'll see that they're both lazy, but Java streams have more of a pull-based model, whereas reactive streams have more of a push-based model. Actually, they can have both push and pull, but we'll talk about that when the time comes. So you can see here that Java streams iterate internally and invisibly from the point of view of the work you have to do as a programmer between aggregate operations. So what's happening, this is what's called internal iteration, and we'll talk more about internal iteration later and compare and contrast it with external iteration. The reason why they use internal iteration is because, number one, it just is easier to write syntactically, and number two, it allows transparent optimizations. You can do all kinds of cool optimizations, including parallelize things efficiently and transparently. And there's also just fewer accidental complexities because you don't have to write as much code. When we talk about the different models of iteration, internal versus external iteration, I'll talk about the pros and cons of each approach. But be that as it may, with Java streams that uses internal iteration, as well as with Java reactive streams as well. So what would be an alternative way of doing things? Well, it turns out that the more conventional way of doing stuff, the world before streams, was by using collections that were explicitly iterated through using various loops and or iterators. So here's a very simple example that's the same code we see here done in the classic way, the object-oriented way, as opposed to the functional streams-oriented way. And as you can see here, we have a couple of for loops. We have a bunch of if statements. We have a lot of code that isn't really integrated. You don't see the fluent interface style of programming. Everything is done in a more ad hoc way. And as a consequence, there's a lot more opportunities for accidental complexities to arise here. And it's also very easy. It's actually a lot harder, to perform transparent optimizations. You can't come along and make this code run in parallel without enormous amounts of explicit surgery on the code itself. So much more effective to do this kind of program than this kind of program, even though this kind of program is probably something that's perhaps more intuitive to you at this point. One of the goals of the course, by the time you're done with the course, you'll be like, yuck, I wouldn't want to write code like this. This is the kind of code I want to write. And if you have that feeling by the time you're done, I will feel very pleased that I've helped to get you to the stage where you can be effective as a functional programmer, and perhaps more importantly, as a parallel functional programmer with the modern Java frameworks. So that's the end of the overview of some of the common Java streams operations. As we'll see, there's a lot more here than meets the eye at first glance. And so my goal is to introduce you to these concepts kind of a little bit at a time, so it seems more seamless to learn them as we go through the different modules and lessons.